Welcome to another video explaining the universe using the particle model. Today's video is titled Equations for VG1 and IfR. VG1 is volts per G1 and IfR is the interaction factor for a resistor. I've tried very hard 3 years ago to get these equations and could not. But first, a message about our book. Yeah, that's our logo, a large apple representing gravity 1, a Newtonian gravity, and a smaller apple inside the large apple representing a smaller but faster gravity that we propose in the particle model. The title of the book is Principia Mathematica II. It's available in paperback for $34 or almost $35, as an ebook for $3, and pretty soon there'll be a hardcover book available, fortunately, for more money. You can purchase these books by going to this link, tpm.thehilster.com. Well, I've been going over a list of words, and part of one of the words I've been doing has been equations, and in the equations was asked by one of my viewers, what about equations for the particle model? These in red are the few I've done in the past. The most recent one was about the Pioneer anomaly, which the word here is anomaly. And now this word is equation, and in particular, it's an equation that I looked for in 2019, did an experiment, and actually had quite good results with the experiment. We could never find the equation for these two terms. So speaking of experiments, and I need to review some of that what I did 3 years ago. I did 3 circuit experiments. Experiment number 1, 2, and 3R. This is the link. I'll put that in the description so you can go find them. Then I did the experiment, and I reported about the experiment, but I didn't give the results. But finally, I gave the results in a second video called 3R experiment results. Quite good results back then. The circuit was a battery and 3 resistors, and I had a large resistor, a medium resistor, and a small resistor, and I was comparing the voltage drop across these resistors when they were in different positions. And here's a typical picture of the one. In fact, this is from one of the videos. A battery at generally 9 volts, G1's flowing through. I placed a large resistor here, a medium, a small resistor here, and you can write these equations for the equations around the circuit. And there's 4 equations here and 5 unknowns. You can't solve for something like that. You got to have the same number of unknowns and equations to hope for a solution. Well, I worked it out with, I had 2 circuits, one with the resistors one way, then one with them flipped. I ended up with 7 equations and 7 unknowns, and I should have been able to solve it. And in general, I could solve the equations, but I could not separate these 2 terms. It just wouldn't work. They hung together like glue. Could not solve the equation for VG1 nor IfR. Well, in this experiment, the first experiment compared whether the voltage value of the large and small resistors were, when placed in the first and last positions, were higher or lower. Actual values were ignored. I just compared over under. The large resistor had a 73% correlation to what was predicted, and the small resistor had an 86% correlation. I used a 6.5 digit meter. It was accurate enough for this experiment, and then the results of the 15 calculations. I had 15 different circuits of different values. And I was hoping for a correlation of 50% and actually got 73 and 86. If the meter was accurate enough, maybe I'll get some good values. Well, here's the, looking at the large resistor, I measured the voltage when it was in the first position and the third. It should be smaller here, because you get loss around the circuit. So I'm looking for a positive answer. 15 different circuits. These are the voltage measurements in the first position of the, and this is the voltage measurement in the third. You subtract this from this, and it's not right. Didn't meet the prediction. Red is wrong. That means 4 are wrong or 11 are right out of 15, which is where the 73% comes from. You could argue about what to do with these two that seem to come out exactly the same. Kind of ignored them in a way, but that's a pretty good result. Then I looked at the small resistor in position 1, then in position 3. And again, I thought they would be positive, but I was wrong. It turns out that the values of how many G1s are flowing around the circuit changes when you switch those resistors. As a consequence, the calculation predicted that they would be negative and only turned out positive. So that's 13 out of 15 were right, giving an 86% correlation. The circuit calculation, the equations predicted negative. I got negative except for 2. Great results. That would happen almost 3 years ago. Well, since then, very recently, I found a value of VG1 times RFR. Didn't find the individual values. I found the product of the two. And last Thursday, a week ago Thursday, October 28th, I was on my morning walk when I remembered about this number, and I was thinking, I wonder if that would help me with the equations for VG1 and IfR. And I had, back earlier before this, I had released this video titled TPM Equations. And it shows the value of A is to be equal to the current divided by this number. This is a key equation, which I'm going to use a bit later. And you can watch this video and see how I explained that. Well, the result is, what I did was, there's a definition of how many coulombs pass a point in the circuit in 1 second if the current is 1 amp. And when I did this, when I went through this whole process of using this idea, I found out that the value of VG1 times RFR equaled this number. What I did was I selected VG1, I adjusted IfR until I got the right answer. What the right answer is explained in the other video. In fact, I think I'll cover that a little bit later. In fact, right now I'm going to cover it. This is what I did. The number of electrons passing a point in the circuit in 1 second is 6.24 times 10 to the 18th, a very large number. And so I took a circuit with a 10 volt source in this case, and a 10 ohm resistor, 10 volts, 10 ohms. That's a 1 amp calculation. So this is a 1 amp circuit. I started out with an arbitrary number, let it stabilize, and I find out that the value of A is this number. This is repeated here in scientific terms. But it turns out that I had to estimate how long a time it took the G1 to go around the circuit, and I've been estimating that as 1 nanoseconds, which means to get 1 second worth of motion around that point, I have to multiply this number by 1 billion. 1 nanosecond happens 1 billion times a second. So you multiply 1 billion times A. Where's my pointer? Come on. 1 billion times A, and you get this number. And I did a ratio, and so I pick this number. I adjust this until I get this equal. And I did it 3 times with VG equal 0.1, VG equal 1, and 0.01. And the product always came out the same. I always got the same number for the product. Amazing. Now, that's what I remembered on my walk. And I'm saying, now, can I apply this value that I just found to the and get an equation for VG1 and IfR? Interesting point, kind of a side point. And you can go through and explain this, but the charge on an electron has this value. You can look it up anywhere. It's this value. You may see a different number down here, but it has that. When you multiply VG1 times IfR, as I did it in that previous example, I get the same number, except I got 27 in that case. I got 22nd, and the power is wrong, but the number is almost identical. And there is a way through that chart I just showed you to explain why that is true. Well, that morning, December 28th, when I got back to my room and did a few things, sat down to do some work, I got my clipboard off, and here's a battery with 3 resistors, and I threw down some equations here. And here I even wrote down an equation for circuit 1 with this is large resistor, small resistor, and then circuit 2 where I switched them. I got 2 sets. Now, I could have started hammering on this like I did 3 years ago and get nowhere. But I wanted to, I put them down anyway. But then I wrote down this number I got. I know it's hard to see, 1.6 times 10 to the minus 10th when there's 1 amp. Then I converted it to 1 milliamp because that's what this circuit had, 1 milliamp, not 1 amp. And so it's 10 to the minus 13th, 1,000 times smaller. But then I did something very straightforward. One of the ways you know how many G1s are lost here is to find the value of B and subtract C. Okay, that's one way. The second way to do it is to just use the equation here for B. The loss is B times IfR times R1. So I have the loss, I can calculate the loss using B times IfR times R1. I can also calculate the loss using B minus C. And since these 2 losses have to be the same, I put them together. IfR appears by itself without VG1 in this equation, and I can solve for IfR, which is B minus C over B times R1, and then VG1 is this magic number divided by IfR. Amazing. I actually got equations. Well, this is a better picture of how I did it. You measure the voltage across here. You measure its resistance. You get current. You calculate B by dividing the current by this number. Remember, that was the prime equation I got in the previous video, that the value of B or A or C is equal to the current divided by this number. Same thing for resistor 2. So I found B and C, and I know that the difference between B minus C is the same as the loss through the resistor. And these are the 2 equations. Man, I was so excited. I immediately told David about what it was. Well, by the time the next day happened, my I decided to test this out a bit. I got some old data from that 3-hour experiment. Use it to calculate VG1 and IfR, and wow, it was terrible. Terrible. Not only were the numbers all over the place, but this one is negative. What that means is that C is larger than B, and somehow the current's increasing as you go around and you're expecting losses, and it increases. No, that's wrong. This is wrong. Something's wrong. Well, either the theory is wrong or the measurements are bad. The theory, the number lost in the resistor is equal to the number in times IfR times R, which is the simple equation. Is that right or wrong? Maybe there's something's affecting IfR or the resistor. Now, I've learned in the past, working on diodes and transistors, that speed is a factor. I'm wondering whether speed affects this IfR or R. More logically, it should be affect R doesn't change. Temperature can change R, yeah, it's there. Initially assuming that it's going to affect IfR. And measurements. The measurements I made back 3 years ago, even though I had a 6.5-digit meter, very accurate. I did 2-wire measurements. And I found out in a video about a month ago that 4-wire measurements are more accurate, and maybe that's the problem. And so I'm just gonna review my measurement techniques. And when you measure voltage, it's not much you can do. The voltmeter has a very high resistance, and so it doesn't steal much of the current. But when you measure something, you change the circuit. But you don't change it very much, and there's not much you can do about that. So voltage is a 2-wire measurement. But measuring resistance, this video made by Keysight shows that with a 2-wire measurement, you get an error because of the lead resistance. And they found that by connecting it this way in a 4-wire, you can eliminate this lead resistance on the outside by having the voltmeter just on the inside around here, and the current that's supplied is on the outside. This is on the outside, and because this is very high impedance, this is almost zero current here. And so you get a better measurement. Here he shows an example of measuring a 1 ohm resistor. 2-wire gets 1.06. 4-wire, he gets 0.995. A lot closer to 1 ohm, and presumably that difference is the lead resistance. So I'm going to be doing 4-wire measurements on my resistors, standard voltage measurements, and see what goes there. The other thing I'm going to do is a test. This is a simple circuit where I'm going to get a 1 ohm resistor, place it here, and measure the voltage across this. And if I know the resistance, 4-wire resistance of this 1 ohm resistor, when I measure the voltage across this, I'll know the current. I'll use a voltmeter to measure the resistance. So I have the current based on a 4-wire measurement, and the voltage on the 2-wire measurements. I divide the voltage by the current, I get the resistance, and I'm hoping I'm going to get a more accurate resistor value no matter what the resistor is. And then I'm going to do a test circuit. This time I'm not going to look for over, under, or switch particularly. What I'm going to do is I'm going to place 1 ohm resistors around. I'm going to measure each one with a 4-wire. I'm going to set this value such that I get 1 milliamp and run the circuit, run it. I'm going to measure the current here, 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 and it should get smaller as it goes around. See how that works. I can also adjust it. I have a power supply that I can adjust, so I can start out with like 5 volts, 10K, get a half a milliamp, then 10 volts, 10K, and get 1 milliamp, and so I can do see whether these resistance values change as I increase the current. Does the speed increases as the number of G1s go through them, just like in the diode and in the transistor. So there's really two different tests I'm going to do. One is to make sure that the current reduces as I go around, and the other is to see what the speed has, what effect speed has on the resistor values. This is just a reminder. It took me like I said, 3 years ago, I couldn't develop this, but it wasn't until I came up with a correlation between 1 milliamp and this value times 10 e to the minus 10, or for 1 milliamp, this same value, e to the minus 13. And so I'm going to be doing this experiment in the next few days, and hopefully I'll get back to you on a video explaining those results, good or bad. My name is Bob D. Hilster, and I am your particle model guru. If you have a question, ask Particle.